Welcome back. Let's do a Matlab example about the high order performance recovery that I covered the theory in the previous video. I would like to use for this example this mass spring damper system that I used about a couple videos before when I covered the Matlab example for the high order adaptive control case. If you remember from that video, we can write this system into this format. A appears like this, B appears like this, lambda is 1 over m, and W0 is basically including this unknown spring and damper constants multiplied these known bases. If obtaining these equations of motion is basically I covered before, so I don't want, in order not to be repetitive, I am just writing the structure like this. A is known, it includes nothing, and since I also consider that B is known, I include all uncertainty to the lambda. In other words, for this system, I consider that alpha, beta, and m are unknown. Nothing is known about this system. All right, I designed some nominal controller, and I designed the adaptation that comes from the former related Matlab example for adaptive control case. The only difference that I do in this video is that I include this V signal, performance recovery signal. We derived this structure in time domain in the previous video, and this basically taking the error signal, right? Error signal. We compute this F and G, which produces this performance recovery signal, and we inject this performance recovery signal inside the control signal, as well as we modify the reference model for the good reasons I explained in the performance recovery video that I posted before this video. If you haven't watched the performance recovery video, please watch it before. You can stop the video here, watch the previous video on the playlist, Adaptive Control and Learning, then watch this video. This way you will have a better understanding. As I always do in my Matlab example videos, basically here is the Matlab code. This slide and the next two slides will give the code. You can take this code, implement in Matlab as it is. It will be a combination of 3 pieces. Total simulation time is 40 seconds. This is the first order Euler methods discretization sampling. In contrast to the video, right, I mentioned I used this mass spring damper example in the adaptive control high order video. I select mass alpha and beta terms to be significantly larger than this video. I just would like to make the system perform worse, right, for you to understand better performance recovery aspect. This was the A and B matrices, this was the lambda, this was the W0. I choose initial conditions to be 0. I use the same K1 and K2 that I covered in the Matlab example for the high order adaptive control example. I consider this 0 for the initial condition for the modified reference model. As you will see in the next slide, I also implement the ideal reference performance just for you to visualize things. It doesn't play much role in theory. And this is the basically gamma, lambda, P matrix, and W hat initialization. This lambda capital basically is the lambda matrix unknown control effectiveness matrix. This lambda is the performance recovery terms at gain. So these are different. I don't treat them to be the same. As I give you some insights that, this is the square wave, right? Basically looking like this. Instead of directly applying like this, I just filter it through. I just apply the filtered version of the command to the actual system because we really don't want sudden changes in the dynamics. So to achieve a smoother behavior. If you like, ignore this, and after you ignore this, call this CCCC. You can apply the same code like this to the system. You are going to see, in this case, control signal will have more sudden changes. Since we should avoid this, I just implemented with a filter in contrast to the Matlab example for the adaptive control high order case. Anyway, so this is the FGV, performance recovery signal, nominal control signal, adaptive control signal, and total control signal. So total control signal, I wrote it like this, but as I explained in the previous video, U is UN plus UA plus V. I already include V inside the UN here. So basically total control signal, if you don't include it like this, you have plus V here. But since I included V here, total control signal already includes V. And this is the reason, I mean, yeah, so basically at the end of the day, U is the minus K1X plus K2C plus UA plus V. I just coded slightly different, that's my point, but it means the same thing that I explained in the previous video. Anyway, this is the XR that we use in here on the performance recovery signal as well as the adaptation signal. I also included ideal reference model signal, basically XRI dot equals to AR XRI plus BRC. And this doesn't include that modification here, and I only included this for plotting purposes to show that as we increase lambda of the performance recovery signal, we approach to the ideal behavior and nothing else. And this is the X dot dynamics, and this is the data recording purposes, and this is for the plotting purposes, and you can basically pause the video and take the screenshots so that you can code exactly the same thing for your research education needs. All right, let's start. Well, here is the position state of the mass, its velocity x2, and it's the control signal as a function of time. Here I choose the adaptive gain gamma to be 1, and I didn't use any performance recovery signal. If you run this code longer than 40 seconds, you are going to see that we will approach eventually. X1 will perfectly track the ideal reference model here. And again, this blue is the XRI. As I mentioned here, I am basically plotting XRI ideal reference model behavior only for plotting purposes. But if you use gamma equals to 1, if you simply add a non-zero V, meaning that you implement the performance recovery signal and choose lambda to be 1, performance is terrific. You basically achieve a much better performance with the performance recovery signal, V. So this shows the promise and importance of this performance recovery aspect in adaptive control. You don't need to wait sufficiently long. You can achieve a very good tracking performance even with lambda 1. If you run this code for yourself, select lambda equals to 0.1, lambda equals to 0.2, and all the way up to 1, you are going to see that you approach the ideal performance as you increase lambda more and more. You don't need to select to be 100 or 1000, as I mentioned at the end of the previous video. All right, so this is the gamma equals to 10 case without performance recovery. I mean, we achieve a good performance right here when we increase adaptation gain. We have slight performance error, the difference between the ideal reference system performance and the actual system. Now, if you implement performance recovery signal, even with lambda equals to 1, you achieve a much faster performance. So basically what you are doing here, right, as I mentioned in the previous video, I told this many times, when you have performance recovery signal, its purpose is to cancel, is to suppress the error coming from the learning process. So basically, you can much faster converge to the ideal performance while learning. So this is the third case. I did something interesting. I added a leakage term. So basically to the parameter adjustment mechanism, now I added the W hat term. So basically W hat dot equals to gamma sigma E transpose PB minus W hat term. I just added this. Of course, when you edit this leakage term, the performance will recover if it recovers a little bit. But basically, I mentioned that this method can be used to recover the performance even when you have high leakage terms, or if you have high neural network approximation errors for the neuroadaptive control case. So here, basically, again, I consider the same case here. You still have this leakage term minus W hat. When you implement performance recovery signal, again, the left was without performance recovery, right with performance recovery. Even with lambda equals to 1, you can achieve a nice performance, and basically you can address the performance degradation coming from the leakage term. All right, I strongly encourage you guys to implement yourselves, right? I give you the codes. I explained until this video adaptive control, neuroadaptive control, leakage modification, projection operator, neural networks, and everything. Performance recovery, if you want to remember something from this video, performance recovery is to recover the performance under, you can have a poor transient performance, you can use this method to recover the performance. You can have neural network approximation errors, you can use this method to recover the performance. The structure of the performance recovery signal V will not change. If you incorrectly select leakage term gain to be high, you can also use this performance. So this is a very powerful method. And just try it, right? So in controls research, I try to present everything with proofs and theorems. I give the stability analysis. Try on your own and let me know what you think. All right? Take care.